Inside an electron ionization mass spectrometer, molecules enter a high-energy environment. They are bombarded with a 70 electron-volt beam that shatters them into unstable fragments. Usually, this massive injection of energy causes predictable damage. The molecule breaks along its weakest points in simple events like alpha cleavages, shedding unstable radicals to reach a lower energy state. This mass spectrum for butyric acid shows the intact parent molecule at M/Z88 on the far right. This towering signal sitting precisely at M/Z60 dwarfs the parent peak, marking the most abundant ion to reach the detector. Mathematically, dropping from an 88 mass parent to a 60 mass fragment means losing a piece weighing 28 atomic mass units. In simple homolytic cleavage, an even mass parent ion loses an odd mass radical, leaving behind an odd mass cation. Subtracting an even mass fragment of 28 to get an even mass ion of 60 violates the basic rules of simple radical loss. This dominant peak emerges from a complex, highly coordinated internal rearrangement rather than random collision damage. To understand how a molecule coordinates a reaction with itself while flying apart, we have to look inside the instrument where the ions are born. This schematic outlines an electron ionization source. The critical event happens right in the center, where the incoming vaporized sample intersects with the dotted red electron beam. When a fast-moving electron from that beam grazes the analyte, it knocks one of the molecule's own electrons out of orbit. The molecule becomes a radical cation, carrying a positive charge and a highly reactive unpaired electron. This state is temporary. The radical cation possesses tremendous excess internal energy. Within microseconds, it will snap apart to relieve that stress. Yet in that microscopic window of time, the molecule is a physical object with moving parts. Its carbon bonds can rotate. If the chain is long and flexible enough, it can fold back on itself, allowing the reactive head to collide with its own tail. This self-reaction is called the McLafferty Rearrangement. It does not happen to every molecule. It requires a specific molecular architecture. The primary requirement is an electron-deficient pi system. Most commonly, this is a carbonyl group, a carbon double bonded to an oxygen, that has just lost an electron during ionization. This drawing maps the positions along the carbon chain. The first carbon attached to the carbonyl is the alpha position, next is the beta position, and the third carbon out is the gamma position. For the rearrangement to occur, the molecule must possess an aliphatic side chain that is at least 3 carbons long. That chain length ensures there is a crucial target available, a hydrogen atom attached directly to the gamma carbon. A chain of 1 or 2 carbons is too rigid to reach back. 3 carbons provide enough mechanical slack for the chain to curl into a loop, bringing the gamma hydrogen within physical striking distance of the radical oxygen. If a molecule lacks a double bond, or if its carbon chain is too short, the geometry fails. The specific atoms can never align in 3-dimensional space, and the rearrangement is physically impossible. When the geometry does align, the molecule drops into a 6-membered cyclic transition state, triggering a cascade of electron transfers. In step 1, the blue fishhook arrows represent the movement of single electrons. The radical oxygen atom is highly electronegative and actively seeking an electron. It acts as an electrophile, reaching across the gap and abstracting the gamma hydrogen across space via homolytic cleavage. The sudden theft of that hydrogen initiates a downstream consequence. The electron from the broken carbon-hydrogen bond swings down to form a new double bond. This structural shift cascades into the adjacent bond, cleanly snapping the connection between the alpha and beta carbons. The tail end of the original molecule has now broken free to form a molecule of ethene. Because all the single electrons have paired up during the cleavage, this expelled fragment carries no electrical charge. It is entirely neutral. Mass spectrometers can only manipulate and detect charged particles, so this neutral fragment is swept away by the vacuum pumps. The cleavage of the carbon framework at the beta position is the direct mechanical consequence of that initial hydrogen abstraction. A molecule in a mass spectrometer has dozens of ways it could break apart. Why does this specific mechanism outcompete simpler cleavages to create the massive base peak? The answer lies in the portion of the molecule that retains the positive charge and actually reaches the detector. What survives is an enol radical cation. It contains an alcohol group sitting directly adjacent to a carbon-carbon double bond. This arrangement allows for resonance. The molecule is constantly shuffling electrons, meaning the positive charge isn't trapped on a single atom. it spreads out between the oxygen and the carbon framework. By delocalizing the charge, the enol structure dramatically reduces its internal stress, transforming what was a volatile radical into a stable ion. Standard homolytic cleavages create primary radicals with localized, concentrated charge, fragments that are energetically expensive to maintain. This stability acts as a kinetic sink. Once the molecule folds and falls into this low-energy configuration, it stays there, driving the massive accumulation of ions at this specific m/z value. Is this precise six-membered transition state an exclusive property of oxygen-containing functional groups? This reaction scheme details 1-pentene, an alkene. It contains no oxygen atoms, yet it undergoes the exact same process. The architectural motif remains the same. The carbon-carbon double bond provides the electron-deficient pi system, and the chain is long enough to furnish an available gamma hydrogen. The molecule curls, the hydrogen transfers, the beta bond cleaves, and a neutral alkene is expelled. The resulting signature peak for this alkene registers reliably at m/z42. This behavior scales up to much larger aromatic systems. Even when the carbonyl is attached to a bulky benzene ring, as long as the side chain meets the structural requirements, the rearrangement proceeds. The McLafferty rearrangement is a universal physical law of gas phase geometry. If the pi system and the gamma hydrogen align, the beta bond will break, whether in a simple alkene or a complex aromatic ketone. For an analytical chemist, this physical predictability brings theory back to the practical task of identifying unknown substances. We can return to the initial spectrum of butyric acid and clearly interpret that massive peak at m/z60. Recognizing these values, 44 for aldehydes, 58 for methyl ketones, and 60 for carboxylic acids, enables an immediate structural diagnosis. These peaks definitively prove the exact length and branching of an invisible carbon chain attached to the functional group. By mastering the quantum-level geometry of the transition state, chemists have turned chaotic gas phase fragmentation into one of the most precise tools for molecular elucidation.